This represents the volume of execution instructions a modern CPU handles simultaneously. At any given moment, hundreds of distinct data paths move through the hardware, creating a chaotic environment for concurrent scheduling. The .NET ecosystem reflects this complexity, offering 20 distinct tools for managing threads and application state. Selecting the wrong primitive from this list will not trigger a compiler error. Instead, they cause silent runtime failures, severe system deadlocks, and performance degradation. Mastery requires organizing these tools into 4 strict architectural quadrants: raw execution, synchronization, high-level parallelism, and state management. The first quadrant, raw execution, is the legacy foundation of .NET concurrency, containing thread basics, join, sleep, and priorities. Understanding modern C# requires tracing the evolution from this manual OS-level control to declarative, high-level orchestration. Basic thread instantiation via new thread carries a specific hardware cost. The operating system must allocate a 1 MB memory stack for every thread execution context. The isBackground property determines the thread lifecycle. A foreground thread acts as a tether that keeps the primary process alive, while a background thread terminates the moment the main method ends. When using thread.join, the primary execution path halts. It functions as a roadblock, forcing the main thread to sit idle until the secondary thread resolves and merges back into the timeline. Thread.sleep creates a similar inefficiency. It traps the thread, holding on to its 1 MB memory allocation while the CPU performs no work. Thread priority settings suggest an execution order to the OS, but under heavy load, the system scheduler often ignores these suggestions to maintain overall stability. Because manual thread management is expensive, engineers required a system that recycles execution paths rather than destroying them after a single use. Concurrent programming faces a central hazard, the race condition. This occurs when multiple threads attempt to mutate the same shared state simultaneously, resulting in corrupted data. The lock statement and monitor class provide the baseline defense. They create a synchronization block where only one thread can enter at a time, forcing all other threads to pause at the boundary. A semaphore manages capacity rather than strict exclusion. In this configuration, the gate allows 3 threads to enter the boundary. A 4th thread must wait until one of the internal threads exits. While locks are limited to a single process, a mutex can bridge entirely separate .NET applications by using a global lock managed at the operating system level. For maximum precision, the interlocked class moves away from software locks. It executes atomic read-add-write operations in a single, uninterruptible hardware motion at the CPU instruction level. Synchronization performance scales based on the operational scope, from hardware-level atomic instructions to application-wide constraints and global OS boundaries. Modern execution moves away from manual OS threads toward the task parallel library. Here, task objects act as lightweight work items that the CLR thread pool dynamically routes to available hardware resources. Tools like Parallel.4 utilize this library to automatically partition large datasets, assigning each segment to a dedicated active core for parallel processing. This data parallelism is ideal for CPU-bound tasks, but I/O operations like database or network calls require a different strategy to avoid blocking threads. This is the mechanics of async await. When a task hits an I/O wait state, it yields its thread back to the pool and leaves behind a lightweight state machine marker. Once the I/O operation finishes, any available thread from the pool can pick up that marker and resume execution exactly where the previous thread left off. By freeing up threads rather than trapping them in blocking wait states, async await increases the total volume of concurrent requests an application can handle. Architectural safety is best achieved when the developer avoids writing manual synchronization locks altogether. Thread-safe collections, such as concurrent dictionary, provide internal abstractions of the locking mechanics discussed earlier, handling safety automatically. The producer-consumer pattern uses a blocking collection to stream data between tasks. The collection manages all internal locking gates invisibly, ensuring data moves safely between producers and consumers. Thread local storage offers another strategy. It removes the need for synchronization by giving every thread its own isolated copy of the data. To manage these operations, the cancellation token provides a cooperative mechanism to signal a coordinated shutdown across all active tasks. Relying on these built-in collections and patterns reduces the surface area for human error and prevents the conditions that lead to race conditions. We began with the challenge of navigating 20 different concurrency primitives and the risks of selecting the wrong tool for the job. This matrix maps tools by abstraction and performance. Raw threads and mutexes sit at the high-risk end. TPL and async await occupy the high-performance zone. Today, use interlocked for atomic math, async await for I/O, TPL for iteration, and concurrent collections for shared state. While legacy low-level tools remain available for specific OS integrations, they are no longer the standard for implementing business logic. Efficient C# concurrency is achieved by moving away from manual lock management and utilizing the optimized routing of the CLR thread pool.